Hey everybody, in this next video lesson, we're going to talk about quantized energy and bright line spectra. Now the first thing we want to talk about is quantized energy. In a previous class, we talked about how the electrons occupy these energy levels around the nucleus, kind of like how planets are in orbits around the sun. And as we know, the planets exist in orbits that are a set distance from the sun, and electrons likewise are in a set distance from the nucleus. But how do we know that? Imagine the different energy levels as distances from the nucleus, and we define the distance from the nucleus as how much energy an electron has. So the further from the nucleus it is, the higher the energy. Well, we suspect that electrons were like this, or at least scientists back in the day suspected electrons were like this, because when they shined energy onto elements, they would glow. They've known this for many hundreds and thousands of years. They would glow specific wavelengths of light. Scientists then looked at that light through a prism, spread that light out, and they noticed some really interesting things. That different elements, when you spread their light out, separated into these very specific lines that you see on the right-hand side of the screen here. You've got argon, which separates into a bunch of lines like this, and helium like this, and mercury, and so on. And so how do we get this from atoms under high energy? Well, they made some assumptions, did some tests, and figured out that the electrons must sit on these specific energy levels, otherwise known as quanta, which is why we call it quantized energy, because the electrons are on a specific energy level in relationship to the nucleus. So as I talked about, if you take an element and you warm it up or put some electricity on it, it will begin to glow. We'll talk about how it glows here in a second, but first, what happens? Well, you, as I mentioned, can separate that light using a prism or some sort of diffraction gradient and spread the light out into individual lines. These are known as atomic emission spectra or bright line spectra. These bright lines are assumed to be an electron, specifically one electron that is emitting energy at a specific wavelength based on how far it is away from the nucleus. And what's interesting is that no two elements are identical. Each element has its own signature light spectra. So you actually can identify an unknown element by bombarding the element with energy, either through photons or electricity or something like that, and it will emit light, and you can identify that light because this is the only way mercury presents itself in a bright line spectra, or this is the only way helium, or this is the only way neon does this. This is the same principle behind neon lights or fluorescent lights. The light that you see coming out of those lights are actually many, many different electrons emitting different light in different colors, and the colors are all blending together. It makes sense that neon light, a true neon light, is actually quite orange. It's a bright orange light. And look at down here in this bright line spectra of neon. If you combine all of these different lines, you can imagine they all blend together to make kind of an orangish light. So in summary, scientists know that the electrons are on quantized energy levels because the electrons specifically emit only a very specific color of light. And each one of these lines represents a different electron at a different energy level, or the same electron at different energy levels. I'm going to take a moment now to describe how this works. So imagine you're an electron and you are sitting on one of those energy levels around the nucleus. We say that you are at your ground state orbital. Now, we don't specifically know what an orbital is yet, but we'll talk more about that in detail. It's a fancy word for an energy level or a part of an energy level. But the electrons begin in their most stable state, which we call the ground state. And then a source of energy comes in and basically causes the electron to jump to a higher energy level. So it gets promoted. And when it does that, it becomes excited and unstable. That electron wants to go back down to its ground state. It does not want to be in an excited state. And in order to return to its ground state, it will immediately fall back down. And upon falling, it will release specific amounts of energy depending on how far it falls. The larger it falls, the more energy it releases. The more energy it releases, the different color of light. We'll talk about that on the next slide. But sometimes the energy released falls in the visible spectrum of the electromagnetic spectrum. Sometimes it doesn't. Sometimes it emits energy of light in the ultraviolet spectrum. And this is the premise behind tanning beds and tanning salons. Inside, those lamps are emitting photons of light in the ultraviolet spectrum, which is simulating the UV light coming from a star like our sun. But sometimes the light falls in the visible spectrum, and we see that as different colors of light. The amount of energy release is proportional to the energy level change. The larger the energy level change, the higher the energy of light. The lower the energy level change, the lower the energy of light. I tried to illustrate with my little drawing there earlier, but this is a much better and cleaner drawing. But imagine you're that electron right there, and this energy is going to be absorbed by the electron, and it jumps up to a higher energy level. It is now unstable. It wants to return, and when it returns, it emits that energy in the form of light. Specifically, because it goes from this energy level to that energy level, that corresponds to an energy of light that falls in the red visible spectrum. So when we see that on a bright line spectrum, it shows up as a line on the red part of the spectrum. Now, maybe we absorb a little bit more energy. So same electron absorbing more energy maybe jumps not just one energy level, but two energy levels. So it becomes even more unstable, falls back down to its original energy level that it started on, and it will emit a different color of light because the fall was much higher. Now, this might be the same electron giving both the red and the orange line, or this might be two different electrons because the electrons have the ability to jump and fall independently of one another. One electron might jump one energy level while another might jump three energy levels. And because this is happening so fast and falling back to its original state so fast, and it's happening in a repeatable way, it's like jump, fall, jump, fall, jump, fall, jump, fall, then we see a sustained color of light on that line, and the different lines represent different falls or falls from different heights. And an electron may jump from the second level all the way up to maybe like the sixth or seventh level and have a partial fall. It might fall down a little ways and then jump back up and fall back down in those intermittent, and that might represent a different color of light, or it might go all the way back down to the original spot and emit purple light. And so you don't have to fall from high all the way back down to a ground state because the energy is constantly being fed in. It's constantly being applied to this electron. And because of that, maybe it absorbs some energy before it gets all the way back down to its ground state and then jumps back up to that high state again. If it falls all the way down, it would be purple. But if it only fell down partially, it would be blue. And from there, maybe it falls down partially even again in two stages. So you get purple light, green light, and blue light all from the same electron falling at different parts or from different heights in this energy levels. And if you put it all together, you get all of the different colors of light. There are so many different combinations of electrons jumping and falling either all the way back down to ground state or partially, or jumping up a few and falling back down one, that we have hundreds of different possible ways that electrons could emit light. And as I mentioned before, sometimes that light falls in the ultraviolet spectrum, sometimes it falls in the X-ray spectrum, sometimes it falls in the gamma ray spectrum. Remember, the electromagnetic spectrum is a wide-ranging spectrum of energy that represents all the different wavelengths of light that could possibly be, and our eyes can only detect a very narrow band of that electromagnetic spectrum. So each possible fall is one wavelength of light that is determined by the quantum of energy that falls. This creates a very unique signature for every element. Many of these are not even visible, as I mentioned, sometime maybe even in the infrared or the microwave range. It's possible that they exist, but we just can't see them with our naked eye. And none of this would exist if electrons didn't occupy specific energy levels, which we call quantized energy. Well, that takes care of this video lesson. Thanks for watching.